So this talk is about kind of at the cutting edge of research and I think clinical applications for artificial intelligence and point-of-care ultrasound. Just to give you a little bit of background about myself, I'm Andrew Taylor. Chris Moore couldn't be here. He was also going to help me out with this talk today. But I previously did an ultrasound fellowship and then went back and did clinical informatics. And now I mostly do clinical informatics, but I'm interested in this space, which is I would kind of label as computer vision or artificial intelligence. And so we'll go ahead and get started. So I have no disclosures. The course objectives and what we're going to try to cover today is understanding just kind of the basic concepts of machine learning and artificial intelligence as it applies to point-of-care ultrasound. What are some of the current challenges that you might face or that we're facing within this kind of domain, and then also some of the potential future applications. So many of you probably have heard of machine learning and talk about it. I think the concept is at this point not really novel, but I think this is a pretty good definition. So it says machine learning is the science of getting computers to act without being explicitly programmed. Andrew Ng, I'm not sure if you know who he was. He's one of the founders of Coursera, does a lot of machine learning work out of Stanford. But I think to really understand that, I think it's helpful to see something like this, which is just a basic algorithm. This happens to be a VFib algorithm. But the concept behind this, and as it applies to computers, is that this is really a prescription of our knowledge onto kind of an algorithm or sequence of steps. And the way you would do this with a computer is you would say, if this particular blood pressure was at this particular level, then you do this, then you do that. And that's not really machine learning. It's really just kind of your programming in individual steps. So the core task of machine learning is learning from data. So you're not really kind of prescribing or writing in the knowledge that's been there. You're trying to gather that knowledge or glean that knowledge from the underlying data. And so the idea is you have a data set, you have some type of function or algorithm that's supposed to learn from that data set, and then you have to try to teach it something, which is your objective. Now that objective can be a lot of different things. It can be categorization of plural effusions or not plural effusions, so like a categorical thing. It can be a continuous learning example like automatic ejection fraction. But the idea is that you have a large set of data that you're feeding into it. You have a large set of examples that it's supposed to learn from. And it's kind of this iterative process until it gets down to the lowest kind of minimal error that it can achieve. And that's kind of what it's learned up until that point. So traditional image analysis was a lot different. So it was mostly defined by what I would call as like manual feature learning or feature engineering. And we'll talk a little bit about that. In this process, I think kind of hurt the kind of moving along of this field because it's limited in what you can do, and it's also very time intensive. And I think these examples will kind of show that. So this is just a basic task where you want to segment out something and you want to create basically a border or a label around something. And there's several different processes or algorithms that you have to apply at each step to get you kind of through that. And this only applies to this particular task. So it's only for image segmentation or outlining within this. If you wanted to do something different, if I wanted to, again, like label a particular aspect of something else, you probably would have to write a completely new algorithm and develop a whole different set of software schemas to be able to do that. And that takes time. And so for every individual task that we can think of for point-of-care ultrasound and all of the different applications and categories and values, you can see how that would be a huge problem. Just a little bit more about this and applying it to ultrasound. So this would be kind of image segmentation, looking at the kind of endocardial border, and you could use that again for eventually for like ejection fraction, but you have to kind of prescribe these steps within it. So the solution, or at least what the current kind of state-of-the-art solution is to do it a little bit differently. It's to use neural networks and deep learning to kind of accomplish this task. So I think most of you also probably know, or at least have heard the term a neural network. It's kind of modeled typically kind of off of what's thought to be going on in our brains. So I won't really go into the details of that, but I do think it's important to understand what the deep learning aspect of that is. So traditionally, when you had these neural networks, and I'll go back just for a second, you would have just one or two layers in the middle that would kind of join up the synapses. Deep learning is very different in that it's deep. So you have tons and tons of layers within the middle part of that network from the input to the output. And what that does is it allows you to be able to build up a kind of a hierarchy of features within your learning task. And so within this example, if you can see on the far left, you start out with just basic feature, what I would call feature detections, like you're seeing kind of edges or start of curves or particular color patterns. And then those things in the next layer within the deep learning model get kind of combined into now circles, or for instance, with faces, it would be like noses, and then you combine that in the next layer after that into faces. So it kind of builds up into this hierarchy throughout the model, and it's just a much more expressive way of looking at this data, and it tends to be much more powerful in its ability to make predictions out of it. And I would say probably even 6, 7, 8 years ago, it was not easy to do deep learning research. Most of the stuff was written in kind of lower level programming languages, and there weren't really any what I would call user-friendly packages to use. But now it's really, I think, moved into the mainstream. This is just showing one of the kind of models that you can build out of Python and Keras, which is a programming languages. But it's even moving further than that, where I think we're getting to the point where it's not going to be hard to drop in your data set into something that's already pre-built or pre-configured through like Amazon or Google, and to be able to kind of generate your task out of that. So I don't think that in the future, within the next 5, 6 years, it's going to require a lot of programming knowledge, and didn't want that to discourage you from maybe looking into this area for potential research. So just to give you an idea about how powerful this technique is, this is the MINTS data set. I don't know if you've ever heard of it, but it's basically this large data set of numbers that were taken from postal codes. These are handwritten digits, and it's one of kind of the standards for comparing machine learning algorithms against. And they've gotten to the point, and this is not even that recent, they've gotten to the point where the machine learning algorithms only miss about 0.2% of all the numbers. And you can see some of the numbers can be, some of them are okay, but some of them can be very difficult to recognize. So they've gotten really, really good at this over the last couple of years. And I think, so this has moved now from what was traditionally kind of started out in the recognizing the numbers, and then they moved on to recognizing faces and other images that may have been accruing on the internet. And I think within the last probably 2 to 3 years, it's really moved into the kind of healthcare area, because there's a lot of potential applications. This is just one example where they're using some machine learning and deep learning to do automatic EF calculations within that space. So any questions just up until now? I know that was a lot in a short period of time. So there are a lot of challenges, and I can understand people's maybe frightened, kind of doing some research and moving into this space. And we're going to go through those. So some of it is to do with labeling. Some of it is just the volume of data, and particularly for point-of-care ultrasound, we tend to use or acquire video clips as opposed to what I would call still image clips. And that in turn results in this problem of scale, and we'll talk about that. And then I think there's also a challenge of finding the right kind of application for these things. So labeling. Traditionally we talked about in the very beginning with the machine learning task, you really need to have some type of objective that it's trying to learn. And there can be lots of different things. This happens to just be kind of echo data and whether there's effusions present, whether there's strain present on the RV, whether the aorta and the exit is looking normal or not, and then qualitative assessment of the ejection fraction. So we have this labeling that occurs, and I'm sure it's occurring in many of your institutions with whatever type of kind of PACS-based system and worksheets that you're using. One of the problems is that data good enough overall? Is it being recorded to a high fidelity within the system? You may not even have a worksheet. It may be all dictated, which also runs kind of into problems from that standpoint. So what this ends up resulting is that we have tons and tons of data out there. I'm sure many of you are storing like tons and tons of ultrasounds that aren't really labeled very well. And that's a big problem for machine learning tasks because you can only learn if you have really good representation underneath. So, are there better ways to do the labeling? I think there's several different things you can consider about this. One is how many labelers you have if you're kind of looking into this, doing this task. So we've looked into this over the last year or two and trying to figure out, okay, if you're going to do, let's say, prediction, we're trying to identify whether somebody has hydronephrosis or not. Do you need 2 labelers? Do you need 3? How many is okay? How many will get you to the point where that you're at expert level? And when I say expert level, I would be, like a point of care ultrasound, fellowship trained person, something I think you could bring out to market. So there's that question. And most of our current systems that we have in place aren't recording 2 or 3 labels. No, I don't think anybody's doing QA where you're having 2 or 3 people doing QA on any individual study. And then, what do you do when you have discrepancies between the labelers? So one person says there's no hydro, one person says there is, and how do you deal with that? So those are questions around labeling. The other problem you're going to run into with this is if you are storing video data, it tends to be large, and it tends to have a different quality to it than static images. So it has this time dependency component to it, and that is in itself a different challenge for a lot of these kind of machine learning tasks, and that you have to kind of build in that into your model. It's not just a simple model where you can look at the surface of something and extract kind of the information from that. Now you have to look into these kind of three-dimensional volumetric cubes and looking into those. And there's completely different models that are used for that. And then in addition to that, the video data, with the video data, you run into a problem about scale. And that comes into problems with the storage of the videos and the data, and we'll talk about that, the pre-processing of it. So how do you de-identify it? How do you strip out kind of all the surrounding periphery of it so that you really only have kind of the high quality data within the middle of the image? And then how much you label it on scale. Let's say you have tons of ultrasound images, you know that they're not well labeled. How much you go about trying to get a better labeling process with that. So this is, I kind of push back at people when they use the term like big data for most things. So I usually define big data as something that can't fit on your own individual desktop or laptop, which usually means that once you hit about 64 gigabytes of loading a file into memory, and that would be a large desktop. That's kind of you run out of your capacity to handle anything over that. And now you're kind of in the big data land because you've got to distribute out those tasks and the processing over several computers. And ultrasound data, I mean, I think we're going through kind of the internal process of updating our servers and everything else. And we were told, well, now we've gone over our allotted 2.5 terabytes of ultrasound data, and we're up to like 7.5 terabytes of ultrasound data. So it's huge amounts and volumes of data that your IT department is likely storing for you. And it's hard to process that information without some help. in any individual project, let's say if you just selected, I just want to look at, again, like renal or echo studies for the last 2 years, and we just want to look at the parasternal long axis views within that, you're still going to get into the hundreds of gigabytes in size for that. So it becomes even difficult for individual projects. And again, I talked a little bit about the kind of typical RAM size of computers. So I think this is something where you definitely need to reach out to IT. You need to consider kind of cloud computing services to be able to help you along those pathways. The other thing with the kind of scale of this data is that I'm sure, at least probably most people are not storing this data as de-identified because you're using it clinically and if you need to go back to it. So one of the big questions is, well then, how do I get thousands or tens of thousands of images out of my system, like out of my kind of my particular hospital or system into a different space where other researchers could potentially use it or learn from it, and strip all of the PHI off of it, and get it to the smaller image file sizes. I mean, most file sizes for DICOM, you can be 800 by 600 pixels. You can be even higher than that. And those are going to overwhelm most of your kind of traditional processing things. So getting something down to like 50 by 50 or 100 by 100 or 250 by 250 is a little bit easier to work with, and you might not lose necessarily the kind of data that you need to accomplish the task. So one of the things that we did is we developed a kind of online platform called Ultrasound Pro that you can download. And it basically, you download this Docker container that kind of has all of the dependencies with the software and everything else. And it does a few things. So one of the things it does is it anonymizes all of the video clips, and it does it in batch or bulk. So if you have like 1,000 or 10,000 clips and they're stored in a particular file, it'll go through all of those DICOM files, strip all of the PHI off of them, and then dump it into a separate file that's with complete de-identification. It also does dynamic cropping. So depending on the ultrasound type, so the difference between your like endocavitary probe and its profile of what valuable kind of real estate is for the ultrasound versus kind of your linear probe. Those two things are very different, and if you crop it, if you just took like a standard crop and just cut off the edges, you're going to lose information in one and you might not in another. So it's probably hard to see from way back there, but these are just examples of where we went through. So we took original DICOMs and then we anonymized them, and we looked at all the different types, and then we kind of stripped off the peripheral stuff just to get you to the final thing. So another issue, and we talked a little bit about the labeling problem before, so other things you could potentially consider is doing some natural language processing. My guess is that most of us are using some type of structured kind of clicking through the data within our worksheets for this, and a lot of people aren't dictating into a system, but that's a potential option for doing labeling if that's the type of data you're storing. And then crowdsourcing, I think, is another potential option. It has not really been answered whether just training somebody for 5 minutes to look at a gallbladder to identify, yes, that's a gallbladder, is 5 minutes enough to look at it on an ultrasound image? And if you can do that and you can prove that it only takes that amount of time to be able to recognize one particular small task, there are platforms out there that will allow you to be able to distribute that to hundreds or thousands of people that would allow you to be able to do the labeling a lot easier for these images. And then I think the final challenge, and this is I think where definitely with the point of care ultrasound community can be most helpful, is finding the right applications and looking at do we really want to look at categorical versus quantitative ultrasound findings. And what I mean by this is, I don't find like a particular machine learning or deep learning task that identifies pericardial effusions for patients, but only it's doing it slightly worse than an expert, is not particularly helpful to, I think, most of us and probably most people in general that are, at the bedside doing these ultrasounds. So it really is context dependent. It would be a lot different if you're thinking about it from like a cardiology standpoint, where you have an ultrasound tech that's doing most of the ultrasounds, and then they're getting uploaded into PACS, and you can think about having preliminary reads done by like a machine learning tool during that kind of time frame when it's not overread by somebody. And then I think there's applications within the pre-hospital settings, within remote settings for kind of early users and adopters of these technologies. But I think this is definitely one area where we can help both industry and researchers to kind of find what works and where we should be focusing within these areas. So, for potential future research and applications, I think one of the main things is to think about this from kind of a multi-institutional collaborative. So one of the downsides to the deep learning techniques is that it requires lots and lots of data. And when I say lots, probably for some of this stuff we've been training to look at pericardial effusions, and I think we have about 10,000 images right now. And I think we probably need another factor of 10 above that. So it's very unlikely that you're going to be able to train well a system in one single institution, because these things just don't occur that often. It's not that often that you have pericardial effusions, and you need lots of those training examples. It's not that often that you have like an aortic root dilation, and you need lots of examples to be able to train the algorithm to do that. And so because of that, I think we're going to have to move to these multi-institutional collaboratives to provide information out there. And then I think it's also an opportunity to think about how to do the labeling process as well. And then the other thing I think within this kind of the research applications is really to think about how best is this used. And I talked a little bit about kind of the remote setting versus not, but I think at least the areas where I think we struggle is in the more quantitative aspects of kind of point of care ultrasound. So even for like determining aortic root size, I definitely see people be off by a couple of millimeters within that space. Cardiac output, RV strain. I think from a learning or educational standpoint, trying to determine whether you've done a thorough evaluation of the gallbladder, those are things that I would call like kind of an augmentation of what's already being done. B-line counts or volumes, and seeing whether it actually matters how many B-lines you have, as opposed to the kind of standard cut of 2 to 3 B-lines and that being considered positive. So all of these things I think can be helped by the kind of machine learning and deep learning tools. And I just wanted to leave you with some final thoughts, and then we'll just open it up to questions. So one, automation is happening. My guess is that probably within the next 5-6 years, that a lot of the companies and the software that's coming out will have tons and tons of features that have automation within them. And I think our job, if you don't feel comfortable doing the kind of programming in that aspect of things, I think our job is still a very vital part of things, where we are going to serve as the content experts to provide direction about where that research should go and what actually matters and what's important. And then also, I think this is the opportunity to do some teaching, and this has kind of a unusual form of teaching in that we're teaching some machines to be able to do this and to do this well, and that would kind of go along with the labeling process. So I'll stop there and just open it up for any questions that people might have. And thank you. Questions? Is anybody working on this? Is anybody working with industry? No, not yet. No? Is anybody interested in this stuff? Yeah. What are some thoughts about where this is going? Oh, go ahead.
With the computer vision, excuse me. So, with the computer vision, I know that there's a lot of challenges with lots of data required for doing even 2D images, such as plain X-rays. And I think there was a study out there that was talking about they were using it to do augmented intelligence, where they were able to identify nodules on X-rays and being better able to perform than radiologists. But I assume it's got to be pretty challenging to do it ultrasounds because it's very user dependent. Like, does the deep learning, does that account for all of those? Issues?
And so I think that it's going to be a big problem if the companies that are working on this and the industries are not acquiring images that are being done in the point of care setting, because the quality differences are just from the standpoint of like how clear the image is. There's going to be a difference between that, especially if you're in the echo lab, what the images look like versus what we're doing in the point of care, and that makes a difference. If the machine learning algorithm is only trained on those echoes that are in the lab, its performance within the point of care environment is going to be a lot poorer.
Is the Docker available for download?
Yeah, it is. We just changed it a little bit, so we can put it up, and I can send that out as well.
Thank you.
No, you're welcome. Okay, I think we're rolling over into the next group. Thanks everybody for coming. I appreciate it.